welcome to Engineering Sim. In this video, I will talk about power triangle. Understanding power triangles is a very good tool, because if you understand the power triangle, you can derive complex power equations with respect to the real power and reactive power. And also, the power triangle can be used in power factor correction. So let's see how we can use the power triangle. So first, let's talk about lagging power factor. If we have a lagging power factor or angle, power factor angle. So lagging power factor angle, typically inductive, when you are dealing with inductive systems or inductive system impedance. In other words, when we are saying lagging, really what's implied is the current, if we denote that with I, current lags voltage V. So anytime you hear the word lagging, leading, it's current with respect to voltage. So lagging power factor angle or lagging power factor means the current is lagging behind the voltage. So graphically what that means is, so if you have a plane, so if you have, for instance, current phasor, then you draw the voltage phasor. So for instance, this is the real axis or real part, or whatever you want to call it. This is the J imaginary part. So if we use this as a reference, this horizontal line, so the angle from the reference to the current, we can call that theta I, meaning the angle or the phase angle of current. And then from the reference to the voltage, we can call it theta V. So you see current, so if we assume phasor rotation or the positive rotation in the counterclockwise rotation, you see voltage will go first and behind it will be current. That means the current will lag behind the voltage. So let's call theta the difference between the voltage and current angle. So theta V minus theta I, from here we can see theta V is greater than, theta V is greater than theta I. Then if you take the difference, theta V minus theta I will be greater than 0. So that means theta is positive. So when you have a lagging power factor angle, the power factor angle will be positive. So let's keep that in mind now. Let's derive the equation for the complex power. So S, this is the symbol with a bar on top means it's complex. That means it has a real and imaginary or part. So S is equal to real power plus J times Q, which is reactive power. So what is J? J is equal to square root of minus 1. Q is a reactive power, and some people will call it imaginary power. Some people will call it wasted power. In reality, it's not imaginary. It's something that basically it has to be there to support the voltage, and that means you have to install equipment to do that. That means you have to pay. There's an equipment that has to be paid for, whether it's a capacitor bank, whether it's included in generation, uh, SVC, StatCom, FACS in general. Some equipment has to be installed in order to provide that reactive power. So instead, the correct terminology is reactive power. It's not imaginary. So it's something that has to be there. But anyways, and also, so this is a polar form. We can also write this in this is rectangular form. In polar form, we can write the magnitude of S and also with an angle, theta. And also we know S, basically it's a voltage times the conjugate of current. So these are phasors. And we can represent phasors with their, basically the magnitude and phase angle. So this is theta V times the current. From the previous slide, we said current has an angle of theta I. So the magnitude of the current, the phasor of the current, the angle of theta I, and there's a conjugate here. So when you have multiplication, so magnitude times magnitude, it doesn't change, so we'll just write V times the magnitude of current. And we know, and I would recommend watching previous videos that talk about how to deal with, how to convert from, how to deal with multiplication of phasors in general. So in multiplication, so basically you have theta V, and so one thing before I do that, so this here with the conjugate is equal to, basically the magnitude does not change, but the angle you stick a minus sign. So you put the inverse of the angle basically. So if you want to get rid of the conjugate, basically you put the magnitude with the opposite of the angle. So theta V plus minus theta I, basically. So, and we know the magnitude of V times the magnitude of I is just the magnitude of S. So theta V minus theta I is theta. So basically this theta here is equal to theta V minus theta I, which, so theta is called the power factor angle. So that's the power factor angle. Now, if we have an imaginary axis like J times I imaginary, and we have the real axis here, so the real part, which is, so we have S in general, phasor is P plus J times Q. Q is a reactive power. So P would be some quantity here. So we have P along this axis. Then we have Q, for instance, if it's positive, it's along this axis. Then if I want to write the equivalent of this, you compose a rectangle. Then from the origin, you just draw the phasor. So this is basically S. And this is theta, which is, again, from the previous slide, theta is theta V minus theta I. So the phase angle of the voltage minus the phase angle of the current. And then what we do, we just kind of slide this Q here. Instead, it's the same thing. So instead of dealing with the axes, we just write P, Q. So you see it's that I'm not changing anything. And we write S, power factor angle. So, and instead of writing and sometimes instead of showing the arrows, we just write something like this, like a triangle with a right angle here, and we just write theta, P, Q, S. So this is called the power factor angle. The power triangle. So that's how we construct the power angle or the power triangle. So now we can do some trig, So we know this is a triangle, right angle here, the power factor angle here. We know S is here. We know P is here, Q here. So cosine theta, really just doing some trigonometry. Cosine theta is P divided by S. So for instance, if you are given the power, and cosine theta is the power factor. So if you're given the power factor, you know either P or S, you can calculate the other. So P, we know P is S, the magnitude of S, times cosine theta. Also sine of theta. So sine of theta is the hypotenuse, which is the opposite side, which is Q, divided by the hypotenuse, which is S. So Q is equal to S times sine theta. Tan theta is equal to the adjacent side, which is Q, divided by the opposite side, which is Q, divided by the adjacent side, which is P. And this is very useful. It's used almost always in PE or FE exams. So Q is equal to P times tan theta. This is very useful. This is also very useful. This is very useful. So you don't have to memorize these. If you just draw the power triangle, and you can derive them. And cosine theta is called power factor. So if you are given power factor, you can calculate the angle theta, which is the inverse cosine of the power factor. So that was in talking about lag and power factor. Now let's talk about leading power factor angle. And typically this is found in capacitive systems. So leading, when you hear leading, that means the current is leading the voltage. So let's draw. It's always helpful to draw a picture because it makes it easy to grasp what's going on. So since it's leading, again, when we are talking leading or lagging, we have to make sure we keep what is the rotation, the phase of rotation that's assumed. That's very critical. So in my case, I'm assuming counterclockwise rotation. So I'm rotating in this way. That means current will go first because it's leading, then voltage will be behind it. So again, if this is the reference, then I'm taking the angle from the reference. So this is theta V, this is theta I. So again, theta V minus theta I, so I call this theta. We see that the theta I is, or theta V is smaller than theta I. That means theta V minus theta I is smaller than 0, which means this is negative. So with that in mind, so again, if we do so here's the real part or real axis, whatever you want to call it, is the imaginary part. So if I have a P, sorry, this should be along this axis. So if I call this P, so theta is negative, that means it will be in this direction. So that means if I take, so Q would be negative. So again, if you draw the equivalent, so this would be S. So again, if I slide Q, if I just move it here, scoot it here, so that's Q. So instead of drawing real and imaginary, I can just draw the powers. So I have P here, I have Q pointing this way, and here's the resulting, which is so I have the equivalent or the complex power, and here's the angle theta, which is negative. So you can also derive, so you see cosine theta. In this case, I'm not dealing with angles here. I mean, with negative, with sines. So cosine theta is P divided by S. Sine theta is Q divided by S. Tan theta is Q divided by P. And as I stated before, cosine theta is called power factor. But notice cosine theta is equal to cosine minus theta. So in other words, let's replace theta here with, for lagging power factor, I have theta V minus theta I. For leading power factor, I have theta I minus theta V. So this angle here is positive. For lagging, this angle here is positive for leading, but in this case, theta V minus theta I, in this case, it's theta I minus theta V. So you see, cosine doesn't care about the sign. So that's why when we're talking about power factor, we have to say power factor, and we have to add the word lagging or leading, depending on the situation, because cosine theta is equal to cosine minus theta. So cosine does not differentiate between cosine of an angle versus cosine of minus that angle. So now let's do a quick example. So if we have a load consuming 35 kilowatts at a power factor equal to 0.90 lagging. 1. What is the complex power? Complex power. And 2. What is the reactive power? What is the reactive power? Well, power factor is equal to 0.90 lagging. So I'm just going to put lag. Means the angle theta is equal to inverse cosine of 0.90, which is equal to 25.84 degrees. Note, this is just a note, why it's important to say lagging or leading. That stating the angle only is not sufficient. Note that the cosine of 25.84 degrees is equal to the cosine of minus 25.84 degrees. But by stating it's lagging, we had to choose this angle here instead of the minus angle. So the angle is 25.84 degrees. So again, if I draw the power triangle, I know theta is equal 25.84 degrees. I know P is given is 35 kilowatt. So I need to find Q and I need to find S, or complex power. So again, cosine theta is equal to cosine 25.84 degrees, which is equal to the power factor given in the problem, is equal to P, which is equal to 35 kilowatt divided by S. So I know the power factor, I know P, I can calculate S. So S is equal to P divided by power factor. So 35 kilowatts divided by 0.90, which is 38.89 kVA, because I have kilowatts, so K, or kilo, so kVA. So that's the complex power. And I can do trig, so sine theta is equal to sine of 25.84 degrees. From this little sketch here, the sine of theta is Q divided by S. So I calculated S. So Q is equal to S times sine of 25.84 degrees, which means Q is equal to 16.96 kilovar, or kvar. Another way to calculate Q, if you go back to the power triangle, so I have P, I have Q, so I don't know Q, but I know P is 35 kilowatt. I know theta is 25.84 degrees, and I calculated S. So tan theta is equal to tan 25.84 degrees. So tan is the opposite side, which is Q, divided by the adjacent side, which is P. So Q, this is another way you can calculate Q. So Q is equal to P times tan theta. P is 35 kilowatt times tan 25.84 degrees. And you will get the same result, which is 16.96 kVAR. So the complex power, we know S as a phasor is P plus J times Q. P is 35 plus J times 16.96. So obviously S is kVA. This is in rectangular form. If you want it in polar form, the magnitude of S is 38.89 and the angle is 25.84 degrees, and that's kVA. And also remember S, the magnitude of S is equal to square root of P squared plus Q squared. So if you know two of these quantities, you can calculate the third one. So you can see just by having this power triangle, and remember P is here, Q is here, this is here. There's a lot you can do just with this little triangle here. So I hope you find this power triangle video helpful. Have a great day. Thank you.